Hello everyone, my name is Giannis Fikioris. I'm a PhD student at Cornell University, and I'll present you my recent work, Robust Pseudo-Markets for Usable Public Resources. It was published in EC'23, and this is joint work with Sid Banerjee and Eva Tardos, who are also at Cornell. So first, let me tell you about the reusable resource sharing setting. So there are n agents who, in this example, are sharing a telescope. They're sharing this telescope over T rounds. And in general, we assume that this telescope is an indivisible reusable resource. And indivisible means that I can get half the telescope on one round, and the other agent gets another agent gets the other half. And by reusable it means that different agents have different desired durations. So one agent might want the telescope for 5 rounds, the other one might want for 3 rounds, etc. We assume that the agents demand are time sensitive. So this means that we can't give it for a smaller amount. We also assume, because this is a public resource, we cannot charge money for the agent using this telescope, so we cannot use ideas from standard usual mechanism design. And this model captures a lot of examples in scientific research. For example, as I've been saying, when the resource is a telescope, or when it's a gene sequencer, or when the agents are a computing cluster. And the solution to these problems is usually to simulate a market with some artificial currency. And I'll talk a lot more about this in following slides. So first, let's talk about the model from a single agent's perspective. So an agent I on round T has some duration, KIT, which is how long he wants to use the resource for. A per round value, VIT, so how much value he would get if he gets the item for the desired duration per round. And we also assume that these demands are non-preemptive, which means that we cannot stop, an agent cannot stop using the resource for a demand of a certain round to use it for something else before the desired duration is finished. And we do this assumption because in a lot of settings, especially, for example, the gene sequencer, stopping some demand might not only lead to zero utility, but also negative utility, because the samples being used in the experiments are destroyed and they cannot be reused. So let me give you an example. So in this example, in the first round, the agent has a value per round 1 and desired duration 5. And for whatever reason, he doesn't get the item this round. On the next round, he has a value of 5 per round and desired duration of 3. This item this time he does get the item for 3 rounds he asked for, therefore his total utility is 15. In the next round, he gets a demand that lasts for 2 rounds and it's 8 per round. Now, because we assume that the agent is non-preemptive, he cannot stop using the resource for his round 2 demand and start using for the round 3, even though it would have resulted in more utility. So he is stuck with getting utility 15 over the rounds 2 to 4. And for the next rounds, he gets some utility. On the fourth one, he couldn't have used it. And over the fifth round, he gets something else. And we're going to focus on the Bayesian setting, where these two values, Vi and Ki are sampled from a distribution every round, identical from two other rounds, and independent from what happened in other rounds, and also the distributions of the other players. Okay, so let's talk about the benchmark that we want to maximize. So what, as the mechanism designer, we want to achieve. So first, let me say that it doesn't make a lot of sense to talk about social welfare in this set. And this is because the agent's values are incomparable. So what this means is that because there's no common currency like money, like there is in standard mechanism design, it doesn't make sense to add the different agent values. So instead, we're going to focus on an individual agent benchmark, which means that we want every agent to be able to achieve a fraction of some benchmark. And this is also related to fairness curve. So every agent gets a fraction of something. We assume that each agent I has a fair share alpha I, which is an average 0, 1, and all the fair shares add up to 1. And if agent's fair share so indicates how the fraction of the rounds do we want the agent to get the item for. So ideally. So agents with higher fair shares we want ideally to get the item for more rounds, and agents with smaller fair shares get the item for less rounds. And let me say that the fair shares aren't something we said, it's exogenously defined and it's not a parameter that we can find. So let me give you 2 extreme case scenarios for how to define an individual agent benchmark if you want. So consider an agent who has single round demands and his value is 1 with probability 1, which means that he has value 1 every round. This means that if he gets the item every round here, then his total utility is T, but he shouldn't expect to get a total utility of T because that would mean that no one else gets the item. He shouldn't expect to get nowhere near total utility of T because that means that the other agents get the item very infrequently. And this is especially if he has a very small fair share. On the other extreme, let's consider an agent who has single round demands again, but now her value is 1 with probability alpha I. So it has positive value with very small probability if we assume that alpha I is small. This time, her total utility is alpha IT, but instead, she can hope that she can get close to her total utility alpha IT. And this is because she can achieve this utility, but only getting a fraction of the rounds, which a fraction of the round, this fraction of the rounds is equal to her fair share. So she can hope for somewhere or close to alpha IT total utility. So let's go to the actual definition, and the individual agent benchmark that we use is ideal utility. It was defined in Korok and all in EC'23, and it's related to the Kalais-Morodovsky solution. So this is again an individual agent guarantee, and in order to define it, we consider this simplified setting where agent I is alone, so there's no competition from other agents, but he can win at most alpha I fraction of the rounds. So he can only win his fair share fraction of the rounds. In this setting, in order to maximize this agent should consider some policy, PI, which informs him, given his value and duration in this round, if she wants to get the item this round or not. And this policy should satisfy the constraint that the agent gets at most the item alpha I fraction of the rounds. So we define ideal utility VI star be the expected per round utility under PI star, which is the optimal policy in the setting. So in this setting, the simplified setting where the agent is alone, VI star is the maximum utility she can achieve given the restriction that she cannot win the item too many times. And let me mention that this is a benchmark that's independent of other agents. So no matter what the other agents' values or durations are, or no matter how they participate in whatever mechanism when having, this benchmark is a value that the agent should hope to get or something close to that. And one of the results is that both VI star and PI star, the ideal utility and its optimal policy, can be computed by a linear program. So we can compute this fast enough. Now let me talk about the mechanism that we use to allocate the resource. So we use a first price pseudo auction with multi-round reserves. And it's a lot of words, so I'll explain what this means. The input to this mechanism are the first shares, alpha 1 to alpha n, and a reserve price R. And as I said before, we don't really define the first shares, they are exogenously defined, but we can set the reserve price R, and we're going to set it optimally later. So initially, each agent I gets alpha I times T credits, so credits proportional to her first share. And every round T, we run a first price auction with multi-round reserve R. What this means is that each agent submits a desired duration and a per round bid for that duration, and the highest valid per round bid wins. By valid, of course, I mean that the agent should have the money to pay for her per round bid time the desired duration, but most importantly, I mean that bids that respond to multiple round must be at least a reserve price R. What this means is that if I want the item for a single round, I can bid whatever. But if I want the item for multiple rounds, I need to bid at least R per round. And after this small auction, the item is allocated for the winner's desired duration, and we go to the next round. Next round that the item is available. So, what can we say about the ideal utility guarantees in this setting, in this first price with reserve mechanism? In order to say anything about guarantees, we need to consider what strategy an agent should follow. So we consider this what we call the robust bidding policy, which just says that you should follow pi I star, which is the optimal utility from the simplified setting, which was defined the ideal utility, and just bid the reserve price R every time this policy says that you want the item. So we prove the following theorem, that for any reserve price that's at x1, then no matter what the other players do, even if they're acting adversarial towards agent I, if she follows the robust bidding policy, she can guarantee this fraction of her total ideal utility that depends on R minus a small minus a small term that's linear with square root t. So this is very small, we tend to not focus on it. So if you want to pick the R that optimizes this term, then you should pick R equals 2, in which case an agent can get half of your total ideal utility. And again, this is under adversarial competition by their players. No matter what other players do, if the agent follows a robust bidding policy, then she can always achieve at least half of her ideal utility. So let me give you some intuition about how we get this guarantee. And to do that, let me focus on the reserve price. So if we set the reserve price equal to 1, which is too low because as we said, the optimal thing is to set it to 2, then the other agents can block agent I. What this means is that the other agents, since the player is following the robust bidding policy, can bid slightly above R to get there and ask for really big rounds, and this will mean that they get they can block the agent from getting the resource for the first 1 minus alpha I times the rounds. This means that the agent can only get the good for the last alpha I fraction of the rounds, and that means he is not going to be able to get enough utility out of this small fraction, and then usually the guarantee is really bad. So if we increase the reserve, in this case, if R is 2, then the other agents can win at most about half the rounds. And as a worst case scenario, let's assume that they can win any half of the round they want. So in this case, they win every second round. In this scenario, if the agent has single round demands every round, then it's easy to see how we get the half of ideal utility guarantee. So in this setting, half of the rounds are free, and the agent is gonna demand via the robust bidding policy an alpha I fraction of those free rounds. And since he gets an alpha I fraction of half the rounds, that means he gets half of the total ideal utility. So things can become a bit more complicated if the agent's durations are multiple rounds. For example, if the desired duration is 2 rounds every time. And the problem here is, as you can see, because the other agents can block any rounds they want, there are no 2 continuous lots of rounds to get the item for. And this means that if the other agents can block any rounds they want, the agent is not going to get any 2 slot of 2 rounds. So to fix that, we need to consider the fact that the allocation happens in line, so the other agents can pre-book some rounds, and also to rely on some martingale argument that takes into account that the other agents don't know the agent I's realization of his values. So can we say something about social welfare? And I know I said before that social welfare doesn't make sense in this setting, but it does if you consider a specific setting, which is that the players have equal fair shares and they have identical distributions. In its case, it makes sense to add up the player's values. So fair share does make sense to be tried to be maximized. So it's not hard to show that in this setting, if the agents cooperate in order to maximize the total social welfare, you can show that the optimal online social welfare is at most t times n times p star. And this immediately means that there's always a bound of anarchy, to bound on the price of anarchy, because every player can always follow the robust bidding policy to get half of their ideal utility. So let's talk about an impossibility result, and this shows that there is no mechanism that can guarantee every agent more than half their utility. And here I have to consider there's also like this K-max term, so they can consider half plus 1 over K-max, fraction of their total ideal utility. And K-max is the maximum duration of rounds an agent can ask the item for. And the higher this gets, the closer to half this bound becomes. So this makes that our mechanism optimal, and this is for every mechanism, not just among mechanisms that have a pseudo-market structure. So again, let me give you some intuition for this, and it's going to use ideas from the social welfare that I just talked about. So we have n identical agents with fair share equal to 1 over n each, and each agent is going to have a fair round value of 1 and duration of k max with small probability. So every agent doesn't want the item except for these long blocks of green rounds. And we pick the smaller probability with which the agent has a positive value, such that the fraction of rounds that are green is exactly 1 over its agent's fair share. So here, because of this, its agent's fair share is, its agent's ideal utility is 1 over n, which means that the total ideal utility across all agents and across all rounds is exactly t. So to achieve this total ideal utility, then we need to allocate an agent and the item every round to some agent who has who gets the entire green block of rounds that they want. Unfortunately, this cannot happen because, as you can imagine, each agent's blocks of green rounds are going to overlap with each other. So we're not going to be able to allocate the item every round to someone. And you can show that social welfare here is at most t over 2, which means that at least one agent must get at most half of their ideal utility. So this is all. Thanks a lot for watching. Let me give you a small summary of what I talked about. So I talked about sharing a public reusable resource. I showed the ideal utility, which is an individual agent benchmark. That's the amount that an agent should hope to achieve in this setting. I presented the mechanism to use in this setting, which is the first price pseudo auction with multi-round reserves. I also showed you the robust bidding policy, which is a strategy that an agent can use and which always guarantees half of an agent's ideal utility, no matter what the other agents do. And I also showed you that this mode of half is tight, that there is no other mechanism, pseudo market or not, that can guarantee every agent more than half their ideal utility. Thanks a lot for watching.